When a Hollywood director wants to put a black hole in a movie, they usually hire a concept artist. The artist draws something scary, dark, and swirling, usually a giant whirlpool in space. It looks cool, but it's pure fantasy. In 2014, Christopher Nolan did something different for Interstellar. He didn't hire an artist to guess what a black hole looked like. He hired a theoretical physicist to calculate it. The result was Gargantua, an image so scientifically accurate that it actually generated new peer-reviewed scientific papers. It became the definitive public image of a black hole. In fact, when the Event Horizon Telescope finally captured the first real photo of a black hole in 2019, 5 years after the movie, it looked shockingly similar to Nolan's creation. But the movie didn't get everything right. To make it watchable for a general audience, they had to break a few laws of physics and hide a few ugly truths. Today, we are going to tear apart the CGI of Interstellar to separate the hard science from the Hollywood magic. The science of Interstellar began long before the cameras started rolling. It started with a pact between director Christopher Nolan and Nobel Prize-winning physicist Kip Thorne. Thorne agreed to executive produce the film on 2 strict conditions. First, nothing in the film would violate the established laws of physics. Second, any wild speculations, like the Tesseract or love transcending dimensions, would spring from real science, not just magic. The biggest challenge was the black hole, Gargantua. In standard textbooks, black holes are often drawn as simple black circles blocking out stars. But Thorne knew the math was far more complex. A black hole isn't just a hole. It is a gravitational lens of infinite power. It bends light so violently that it warps the entire universe around it. To visualize this, Thorne didn't just give the VFX team sketches. He gave them pages of equations, specifically the equations for light ray tracing in curved space-time. The VFX team at Double Negative, DNIG, had to write completely new rendering software called the Double Negative Gravitational Renderer, just to process Thorne's math. Some single frames of the movie took 100 hours to render because the computer was literally calculating the path of millions of individual light beams as they got trapped in the gravity well. This wasn't animation, it was a physics simulation. The most iconic feature of Gargantua is the glowing ring of fire surrounding it. This is the accretion disk, superheated gas and dust spinning around the event horizon at nearly the speed of light. But if the disk is flat, like the rings of Saturn, why does it look like a halo? Why does the ring appear to go over the top and under the bottom of the black hole? This is where the visual brilliance of general relativity comes in. You aren't actually seeing a ring above the black hole. You are seeing the back of the disk. The gravity of Gargantua is so intense that it grabs the light coming from the far side of the disk, bends it up and over the top of the shadow, and shoots it toward the camera. Imagine holding a dinner plate. If you look at it edge-on, it's a flat line. But if you placed a bowling ball in the center that could bend light, you would suddenly see the entire back half of the plate lifted up into a vertically standing halo. This is called an Einstein ring. The movie depicted this perfectly. The top loop is the light from behind the black hole being bent over it. The bottom loop is the light from behind being bent under it. It creates a shape that physicists call the hat brim effect. What looks like a 3D sphere of light is actually a flat 2D disk, warped by the lens of gravity. However, this is where Hollywood stepped in. The version of Gargantua you see in the movie is stunningly beautiful and symmetrical. It is also scientifically wrong. Kip Thorne and the VFX team actually rendered a perfect version first, and it looked very different. Because the accretion disk is spinning at relativistic speeds, close to the speed of light, it is subject to extreme Doppler beaming. The gas on the left side of the black hole is spinning toward the camera. The gas on the right side is spinning away from the camera. Physics dictates that the light coming toward you should be blue-shifted and incredibly bright. So bright, it would look like a blinding white searchlight. The side spinning away should be red-shifted and dim, fading into near invisibility. A realistic black hole shouldn't look like a glowing donut. It should look like a crescent moon, heavily lopsided with one side vastly brighter than the other. When Christopher Nolan saw the scientifically accurate render, he rejected it. He felt the asymmetry would confuse the audience. People would think their projector was broken or ask why the black hole was winking at them. So, they artificially dialed down the Doppler effect. They kept the geometry of the light bending, but they equalized the brightness. It was an aesthetic choice that sacrificed truth for beauty. Interestingly, when the Event Horizon Telescope photographed the black hole M87 5 years later, what did we see? A blurry, lopsided crescent, brighter on the bottom than the top. Reality, it turns out, is less symmetrical than Hollywood. The other major scientific plot point was Miller's planet, the water world orbiting close to the event horizon, where 1 hour is 7 years back on Earth. Is this possible? Mathematically, yes. But it requires Gargantua to be a specific type of monster, a supermassive Kerr black hole. To get time dilation that extreme without being ripped apart by tidal forces, the black hole needs to be massive, roughly 100 million times the mass of the Sun. But more importantly, it needs to be spinning. A non-spinning black hole has a chaotic orbit close to the center. You would fall in before you experience that kind of time warp. But a spinning black hole drags space-time with it. This is called frame dragging. It allows a planet to orbit comfortably just above the event horizon without falling in. Thorne calculated that for the 1 hour, 7 years math to work, Gargantua would have to be spinning at 99.8% of the speed of light. Any faster, and the singularity would be exposed, breaking physics. Any slower, and the planet would be crushed. The movie walks a razor-thin line of plausibility, but it stays technically within the equations. Interstellar did something rare. Usually, science movies age poorly. As we discover more, the special effects start to look silly. But Interstellar has aged in reverse. As our real-world telescopes improve, they are confirming the images Nolan and Thorne created a decade ago. The film didn't just use science to make art, it used art to advance science. The code written for the movie resulted in 2 published papers in the journal Classical and Quantum Gravity. It proved that sometimes the best way to understand the universe isn't just to calculate it, but to visualize it. Gargantua is not just a movie monster, it is the most expensive physics simulation ever built.